Today, in the third lecture, we are going to discuss uh, the summary on black body radiation. In fact, it will be quite useful uh, to recall what you have studied during your previous courses on black body radiation, so that you are fresh and you can easily follow your subsequent chapters on lasers. So, in black body radiation, let us look at the concept first. An uh, ideal conceptual black body, as you can see here, uh, is uh, is something which has a black surface, and it should not reflect anything. Neither it should uh, transmit any radiation. It should absorb all the radiation which is coming in. And to better explain it conceptually, Kirchhoff's introduced it in this black body in the form of a cavity. And so that means any radiation which is coming through a hole inside this black body cavity uh, will be absorbed completely. It will not have any chance to go out, as he himself visualized in 1859. Even if some radiation is reflected, it is reflected so many times that, and during every reflection process, some is absorbed. So total sum is that all radiation will be absorbed. Now, Kirchhoff's explained through a law, that the ratio of emissive power, that is emissivity, to the absorptive power, that is coefficient of absorption, for the radiations of a given wavelength at a given temperature is same for all bodies, and this ratio is equal to the emissive power of a perfectly black body at the same temperature. So what he really meant was that even if there are some bodies inside this black body which might not be completely black body, they may have a different emissive power, they may have a different absorption capability, but the ratio of the emissivity and the absorptive power of those bodies will be equal to the ratio of emissivity and absorptive power of the other bodies, and this total will always be equal to the emissivity of the complete black body. So by assuming this, you can relate it with the complete universe system also, assuming this as a global black body, and inside there are number of bodies which are not black, but whatever they are absorbing and whatever they are emitting, the ratio of that, and if summed up with all the bodies inside this black body, then this will be equal to the emissivity of this black body. So this is what is represented here, and we can say that good emitters are always good absorbers, because they are neither reflecting any radiation nor transmitting any radiation. So this holds good for a perfectly black body. Now, uh, now the question was about that how does this radiation takes place, and this was explained by Stephen Baldwin's law. Stephen Baldwin's law explains that the total power, R, which is dependent upon temperature of the body, the total power, which is the rate of emission of energy, E, radiated per unit area of the surface of the black body at temperature T, is equal to the emissivity into Boltzmann constant sigma into T to the power 4. And Boltzmann constant is already given here, and a black body in thermal equilibrium is always having a emissivity of epsilon equal to 1. Now, if the temperature of the body is, let's say, T, and there is a surrounding body also, or surrounding surface which is at temperature T0, that means the body at temperature T, which was going to radiating everything, will now have some radiation which will be dependent upon the temperature T0 of that outer body, because it will be radiating uh, only the net difference between the two. So the formula can be given here in terms of R equal to epsilon sigma T4 minus T04, and it can be explained like this: if the temperature of the body's surroundings are at temperature T0, there will be an exchange of heat energy between them, the surrounding, and the body at temperature T. The net loss of energy from the body per unit area becomes R equal to so much. Now, you can prove this Stephen Boltz's law from the thermodynamics also. And just note, because this laws uh, may not be related to the Newton's law of cooling, because Newton's law of cooling also depends upon the temperature difference between the temperatures of two bodies. So Stephen Boltz's law is mainly for radiation, whereas Newton's law of cooling is for convection. Now, uh, so now we know about the radiation part, but at that time, a number of experimental studies were done during, uh, for black body radiation, and it was found that the black body radiation uh, behavior was something like this. That means whatever emissivity or emission density, emission energy, or the intensity of emission was there, it was varying with the wavelength of the radiation, right? And this wavelength of this radiation had its peak at different temperatures. That means each temperature of this black body had peak at different temperature. So this was the experimental observation. Now this was to be explained by someone, and Wien explained it at that time, and we call it as Wien's displacement law. This states that the black body radiation curve for different temperatures, as you can see 1800, 1500, 1200 and 900 Kelvin, different temperatures will peak at wavelength with the formula lambda x max equal to B upon T, where T is the absolute temperature and B is the proportionality constant, also called Wien's displacement constant. And you can see in this curve here also that as the T increases, temperature of the black body increases, the lambda, the wavelength, where the peak occurs, is reducing, because here you can see lambda is inversely proportional to T. So for example, you can see at 900 Kelvin, the lambda peak, where intensity is maximum, is at around 2800 Kelvin, and at 1200 degrees centigrade it is something around 2300, and at 1500 degree Kelvin this intensity is maximum at the wavelength of around 1900, and when you raise the temperature of the black body further, let's say at 1800 Kelvin, then this goes down, the wavelength goes down to 1500 nanometer approximately, where the intensity is at its maximum. Now this was okay, but the experimental studies shows two other things. One was that it was reducing, the intensity was reducing at lower wavelengths, and it was further reducing at higher wavelengths. Now Wien's displacement law explained as far as the peaking of the maximizing of the intensity at peak wavelengths. But what about the distribution of the uh, spectral characteristics of the radiation? So Wiens tried to explain the distribution of the spectrum of these experimental curves, but he could not explain it very nicely. Although he explained it with a formula which says that a spectral energy distribution, is that means energy for at each wavelength. He explained it in this formula, which says that this spectral energy distribution is inversely proportional to lambda wavelength, right? And since lambda is inversely proportional to t, so it is almost as if E is directly proportional to T in some form. But since he wanted to explain the variation of this spectral intensity with respect to lambda, so he introduced this exponential term. But it was found that Wien's distribution law follows the experimental curves at lower wavelengths, but it does not follow at higher wavelengths correctly. So there was a flaw in Wien's distribution law, right? So that means the experimental observations of black body radiations, especially for spectral distributions, were could not be explained by Wien's distribution law. In the meantime, at that time, uh, Rayleigh and Jeans, they tried to uh, overcome this discrepancy of Wien's distribution law, and uh, they were first to assume that a black body is uh, behaving like more like a cavity, and when they call it a cavity, that means it has a characteristic frequency of oscillation at a temperature, and they explained that each frequency is associated with a mode, and energy in the cavity is allocated among the modes. So that is normal with any oscillation, and its different modes. And Rayleigh and Jeans gave a formula which indicated that this intensity of radiation, here they have explained I. So please ignore this different nomenclatures, and each are related also. Earlier we saw power, which was rate of energy. Then then we talked about spectral distribution, that means E as a function of lambda, and these are related again with the Wien's displacement law. And here also the intensity is again related with the energy of the radiation, emissive emissive energy. So here Rayleigh gave the formula I is equal to T upon lambda 4. So it is similar to the earlier explanations. One good thing was that he explained that this there is a form of cavity in the black body structure, and each having characteristic of a frequency, but he could not explain the complete uh, experimental behavior, and this formula was able to explain only the higher wavelength part. So here you can see the Rayleigh-Jeans formula was able to explain the higher wavelength range of the experimental behavior of black body radiation, whereas Wien's formula, distribution formula, was able to explain the spectral energy distribution of the black body at the lower wavelength range. But uh, one has to still wait for a formula or an explanation which explains the complete experimental characteristics. So then came Planck's radiation law, and Planck corrected these flaws at both ends. Planck postulated that the energy of the oscillators was quantized, and that an oscillator in the cavity can emit or absorb energy only in quanta, that is hf, f is frequency, or hc upon lambda at a frequency. Now that means if higher frequencies of radiation have not been absorbed by the cavity oscillator, it will not emit higher frequencies. And Planck also used Maxwell-Boltzmann statistics like Rayleigh to calculate the radiation intensity, but then he quantized it and thus gave the Planck's distribution formula. And you can see in the previous curve here. See what Planck explained was that if the black body was absorbing energy at this particular wavelength, then it will emit the radiation only at this wavelength, right? And that means if there is no absorption at lower wavelengths, so naturally there will be less emission at lower wavelengths. So it has to be dependent upon the frequency. So the absorption and emission both are dependent upon the frequency. Now, so the Planck's law explains the distribution of intensity of radiation, and here you can see, and if you compare with Rayleigh law formula, then exponential part is uh, not available in the Rayleigh formula, whereas in the Wien's distribution formula, uh, as you can see in the Wien's distribution formula, the exponential part is available. Right now, this Planck's law could explain black body radiation experimental results at all wavelengths, and you can see here, uh, if you analyze this formula at a small wavelengths, that means lambda is much less than hc upon kt. So lambda is much less than hc upon kt, and at that point this part becomes much larger than 1, and so this becomes a the only component here with negative sign, and then it becomes your Wien's distribution law, right? You can see here, because this is ignored, then because this is becomes bitter, much larger than this, so this is ignored, then it has a negative sign, and then it becomes equal to the Wien's distribution law. Now at larger wavelengths, hc upon kt is much smaller than lambda, right? And therefore this total formula becomes almost equal to 1 plus hc upon kt, this one, and so this whole denominator becomes hc upon kt, and it matches with the Rayleigh formula, as you can see here, because h is cancelled, and then you can see here. Now, so the beauty of the Planck's radiation formula was that at lower wavelengths it was matching with Wien's distribution law, at higher wavelengths it was matching with Rayleigh's formula, and that way uh, both the uh, both the regimes of lower wavelength and higher wavelengths of experimental characteristics of a black body radiation could be explained by Planck's radiation formula. So this is what we tried to recall about black body radiation, and now we are in a position to move to the move to study the lasers from next day onwards. So thank you very much.